who will, of course, tell us about his fourth lecture, which is not on this topic.
That's okay. So let's fast forward. So I will talk now a little bit more about how these three things, in my opinion, should belong together. So we have tensor categories, and we have Vertex algebras giving tensor categories, and we have Nichols algebras giving tensor categories, and we were talking sometimes about big picture and things like that. And I want to a little bit do that today, and I also go more into my own research and also a little bit in these big picture things that I said and how much of this we can prove or which aspects. And I've brought even less slides than last time, so I want to encourage you even more to ask. I think it was very nice that we had a little type of discussion, because I mean that's the point of why we're here. Yes, and maybe I want to start with giving a better answer than I did yesterday to two questions that Tomoyuki asked us. Namely, I think it was, I think you asked about the unrolled quantum group, right? What the unrolled quantum group is in that context. I think that was a question of it. And I said the complicated answer because I was thinking about Nichols algebras and not the easy answer. And that was, I want to correct this mistake. So, so what about the unrolled quantum group? So my answer was trying to make the following point, that there is the effect that in negative definite cases, like minus p comma 1, for example, we have that the screening to the p is not equal 0 anymore. That's because there's poles, and the Nichols algebra formula does not hold without modification terms. And the second effect is that you have the effect of G-twisted modules. And so, yeah, something like this. You have also the effect sometimes that this is not equal 0, for example. For example, that Borel is modified. And why these things are connected, I think, is a difficult question, which is what you triggered me asking, but there is a much easier answer to your question. I think the point is, but I think most people here actually know this. The point is, how should you imagine triplet, or Feigin-Tipunen if you want, the kernel of screenings? So it's the orbifold of V lambda by the screening. So it's an orbifold by Nichols algebras. And respectively, the representation category we expect to be a center, Drinford extension of this representation category. And now what is the unrolled? Is the singlet algebra. So this is just the Feigin-Tipunen algebra in lambda degree 0. And what this should be is, well, kernel of screenings and the action of the torus of the Lie group G, because the torus of the Lie group G is exactly the gradient. So this is just the orbifold of V lambda by this Nichols algebra. So you should imagine this as since you have a group acting and you have a Nichols algebra acting, the one actually by long screenings, but not by the ones who are usually called long screenings, but just by the grading operators. So that's the torus acting, and this is the Nichols algebra acting. So somehow these are just two different effects that you can combine. Of course, it's interesting to see anyhow. I mean, you have this, you have some discrete groups acting. I think Milash worked on this in some time, and you also have the continuous group acting, and you have twisted modules and so on. That's a question you can ask, but I think that's all. So that explanation was much too difficult. Yeah, please.
Sorry, I don't know what is the definition of an unrolled quantum group.
Yeah, you shouldn't. So that was just to answer a question that somebody posed, which included the word unrolled quantum group. So if you have the quantum group, you can do two things. You can loosen the restriction that k to the p is 1, and at the same time you can introduce a derivation which somehow unrolls in the sense that before you have q to the n eigenspaces, now you have n eigenspaces. So somehow you separate the different logarithms, so the different n's that q to the n doesn't see. And so this has been introduced for several reasons. So by Blanchet and Guerre and so on, because it makes the associator basically go away that you have if you don't do that. So somehow the thing with the associator came afterwards. So when we realized that you can also do this without unrolling. But in this picture, unrolling simply means you also do an orbifold by this group. And of course, this is an interesting example, but I would be more interesting to put the entire Lie group here. And that's what in my conference talk, I talked about what happens if you put the Lie group here. But that's somehow like the easiest case. We take the torus. That's why this modification here is not violated, just a conformal weights can shift to some irrational number. Good, then let's start. I will do triplet now for a bit. I want to summarize, but we have time. So I have very few slides, but I try to summarize everything on one slide. So what is the setup that you have in general? So with general in particular, I mean also non-simply laced, because several results we saw are simply laced. So this is all, I think, standard notions. So if G is a finite dimensional semi-simple Lie algebra, let P be a number which should be divisible by the lassity. And now we take, and we will see why this is good. Now we take the root lattice divided by square root P, and we take the co-root lattice. So for simply laced, it's just the root lattice. The co-root lattice rescaled by P. And you see so what, for example, is important is that this here is this here is in the dual lattice of this, and this is responsible for this divisibility condition. So otherwise you have a problem at this point. And now what we do is we consider the lattice algebra that belongs to this. So this would be sort of the lattice VOA we work in, and this would be the lattice VOA where the short screenings live in. So this is not in the lattice VOA, it's in some modules. And so we take this rescaled co-root lattice and take the following point. So that's a point in the root lattice. So rho is the y vector, it's the half sum of all roots. This is the dual y vector, so the half sum of the co-roots times p. So usually that's just p minus 1 times rho. This is a point. This is a certain point which is important for other applications in the fundamental alcove, and so a point in the root lattice. And now we take a Virasoro action, which is the standard Virasoro action we had a couple of times for different people on the blackboard, shifted by this background charge, which is exactly q. So what this means is, remember the picture we had from the lattice VOA? This was some parabola, some modules looking the L0 eigenvalue with some quadratic term. This is shifted by q. So we'll see a picture later. So it's a parabola which is sort of has a center around q. It has a symmetry around q, and that's what you should have from the Lie algebra side. So we do that for a reason that becomes clear now. In particular, what you can calculate is the central charge is now depending on this quantity, so it's shifted by this. And if you compute the L0 eigenvalue, that's exactly this parabola I'm talking about. And now let's look at two different screenings. So we have the basis of this lattice. So this is the Vertex algebra. So those are local screenings, and they generate the positive part of the Lie algebra. I'm not sure if for non-simply laced that is proven. I think you have to prove it. So there is some proof in a simply laced case in this Fagin-Tipunin paper, which I think uses a trick that only works for simply laced. So I could not directly give you a reference for this statement, but that's what most certainly we expect. I don't think it's difficult. It's local screenings. And the short screenings, notice I have the other direction, generate now the Nichols algebra. And let's check that they really generate the Nichols algebra by the statement from the last lecture. We have to see, I mean, here, obviously, the scalar products are integer, but they are negative. That's why the commutator is not 0. So the Nichols algebra of these would be trivial, so commutative. But because there is poles, because here I have negative integers sometimes, I have commutators appearing. But that's a standard thing before non-locality. And this is purely non-local. So we just calculate e to the I pi of, there's a p too much, I'm sorry, e to the I pi of this, and you see you exactly get a 2p root of unity times this, and this was the braiding of the quantum. So that's why exactly I did this choice, because that produces this qij. Yes, please.
You can prove that, I mean, this exactly generates the Nichols algebra, not the image of the screen, short screens.
No. So the statement is all relations that hold in the Nichols algebra hold for the screenings, and you can compose the screenings. So we'd expect that this exactly the Nichols algebra. So this is maybe not spelled out. You're right. It's again the same thing. So you can prove all relations hold, and you can compose the screenings, which is not clear. So it's also difficult actually to say they generate an algebra, because you don't know a priori it's an algebra. You prove for every monomial that it converges, and then so actually that's the statement that is correct. The monomials converge and they are 0 if the Nichols algebra has a relation. Yeah. I think so. And you have to check that the subpolarity holds here. And you can check this because you know that this lattice is positive definite and the lengths are smaller than 1. And this is exactly what goes wrong in the negative definite cases. So this is the general picture, and all of these things about why have we chosen them exactly as we've chosen them, because now these elements, if you plug them in, it's an easy calculation to see that the conformal dimensions of the L0 eigenvalue of these elements is 1 and of these elements is 1. So somehow this Q is the only Q that does exactly this effect that the L0 of this is 1 and L0 of this is 1, and this is chosen in a way that it's exactly this. So that's how you get to all these choices. So you want the braiding, you want the Lie algebra, you want L0, 1, that's why you have to put this number. And all of the, when I talk about reflection operators and so on, we have all this respect to this Q. So this is the setup in the general case. Now we go to SL2 shortly. So now the intersection of the kernel of the short screenings. So now I take all elements that are sent to 0, elements in the vertex algebra that are sent to 0 by the short screening, define the Felgen-Tipunin algebra WP of G. And this extends W algebra, so for example, the Virasoro algebra for SL2, which lives in degree 0, but there is more in degree 0. As we see, there is this whole singlet algebra in degree 0. But in particular, you have sort of this. That's somehow how it arises. So people wanted like this affine Lie algebra, this W algebra, and they wanted to have some finite tensor category that sort of extends this, and that's how people thought about why we should build this. So it's an extension of this algebra, which has additionally a G action. So this is infinite, this is finite representation theory, and here there's an additional G action. And you will see the example. It looks. And the big conjecture that we're all talking about is in this field is that the category of representations of this vertex algebra, which is supposed to be a modular tensor category, but we have to prove this first, is a non-semisimple modular tensor category and should be equivalent to representations of UQG, where here I always mean with the associator. So in this way that we've constructed, like remember we started off with vector AQ, and depending on A and Q, there's an associator. So we don't even see the associator, but if you do generate these relations, you notice that you have to do the associator. We don't see it because we did it categorically. I think that's a good approach. And if you do the unrolled one, you also don't have an associator because somehow the ambiguities that you have, which n means Q to the n, these ambiguities are resolved. But I think the way I present this now in hindsight, I think the easiest. I mean, you just start with the right modular tensor categories, which you have from the view. Do what you do. And then one reason why we call this Felgen-Tipunin algebra is because there is this article by Felgen and Tipunin, I think never published. I think it's just in the archive. And then there is this great paper by Sugimoto where many of these statements, probably more statements than I put, are proven. So in the simply laced case, I still put else where there should be else, I think, but so it's not a contradiction. So in the simply laced case, we have an alternative construction by, so what do? What you have is here an action of the Borel part by long screenings. That's this. So this is an action. The other side does not act. So just the Borel part. So the Borel part acts here. And now what you can do from this is, by induction, you can get a bundle over the flag variety. So this is a bundle over GL over LB. This typical thing that you would do when you construct a Rama module as, or an irreducible module as sections of line bundle over the flag variety. Right? You start with a representation of the Borel, and then you get the respective line bundle over the flag variety, and then you take sections, and you exactly get that. Because what you get exactly is somehow what these sections mean is exactly you get somehow all parts of this lattice view A where the action by the Borel can be extended by to an action of GL. So somehow when you have an opposite long screening, and it turns out you exactly have this on the kernel of the short screen, because you can take some divided power of the short screen in the other direction. So that's somehow the idea. So the sections are exactly filtering out which part has a good G action. That's the point, right? And if not, please add something. So it's one here. And in particular, from this construction, you can get a character formula because you can use Euler characteristic and stuff like that. And you can get a character formula, and you can show the decomposition of this with respect to the subalgebra and to this G action, which I should have put. I put it last time. So this decomposes into, this is the finite dimensional module of the Lie algebra G, and this is some module of the triplet of the W algebra. And similarly, as you get this vertex algebra, you also get modules over the vertex algebra. And I put all here simple modules because, as far as I understand, but correct me, I think it's not proven that they are all, right? Yeah, we think they should be all. That's why I put it, but it's not proven. Exactly. But this is, I think, a very different type of argument. So for the triplet, we know that because Adamovich-Milash constructed the dual algebra sort of by hand. You do this until you're finished, and you find enough relations, which is hard work. You find enough relations in the dual algebra until there's only so many modules, and you know you have all these modules. So I think it's a very different type of argument. I'm not sure if we can find an argument like this here, but maybe we can. I mean, of course, having this theory about W algebras, in particular by Tomoyuki Arakawa, you somehow get a lot of control over this algebra, because somehow you look at it as modules over W, and you know how it looks as a module over W, and then somehow you work with the rest. So I think this is the strongest part. So also for proving simplicity and stuff like that. So I think that's what we know about the general case. Questions? So now let's go to SL2. I will have a picture in the next slide. So what does this spell out for SL2? So all this Lie algebra stuff, let's leave it. So we have a lattice view A square root 2pz, which we had on the blackboard last time slides. And this has 2p simple modules, and they're indexed by cosets of the dual lattice, which is 1 over 2p. So there's 2p simple modules. You have the long screenings, those are square root 2p. You have the short screenings minus square root 2 over p. And what the Nichols algebra in this case says is simply that the p power of the screening is 0. So that's the relation we had already in the first slide and the second lecture also. And so this is sort of the trivial case of a Nichols algebra. It doesn't really tell you much. I mean, for a higher rank, it's a lot, right? It tells you the Borel part, which is basically the whole quantum group. But here, this is really a rather trivial statement. Like, think p equals 2, it just tells you the fermion it squares to 0. Right? And now I can take these lattice modules and restrict them. So look, see how they look as modules over the triplet algebra, and they decompose. I have a little bit different notation here than Azad in his work. It decomposes into an extension of sort of irreducible module of the triplet and some reflected irreducible module, except for these cases where they are irreducible. And these extensions correspond to what the Verma module of weight q to the j is in UQS. Okay, it should be j minus 1. It's the convention here is j minus 1. So it's q to the j minus 1. And this algebra has been known before this general cases were around, studied as triplet algebra. So as far as I know, but is the first case where Kausch tried to construct logarithmic CFTs and logarithmic vertex algebras. As triplet algebra, especially p equals 2 is the even part of symplectic fermions. And in this case, now we have a theorem that there is a braided tensor equivalence between this representation and these representations, and there should be an SL2 here. So you can see that. So, and this is work by several people. As I said, these guys here in particular started this, and then Adamovich Milash classified the simple modules, and Tsuchiya Woods, Kreuzig and Runkel started to come up with this in the SL2 case. And then there was the sort of final steps of proving that you actually get a tensor equivalence. So at this point, we already have an equivalence of abelian categories, but this is how you get a tensor equivalence in 2 very different ways. And I will talk about our approach a little bit more because it fits into the big picture. So the approach by Nagel and Gannon, it's in some sense much easier. They managed an arbitrary p at the same time, where we only managed p equals 2. But in some sense, it uses very much that you know SL2 is a category. Here, I think, so I will show you some arguments that I think are much general. That's good that we have different approaches. So they are quite different, both interesting. Yes, let's see how that looks in a picture, and we can talk about this picture a little. So now I've drawn for you the lattice vertex algebra that we had last time. This is this. This is a lattice vertex algebra, but now as you see, the center is shifted to 1. So last time it was symmetric by 0. Now it's a little bit shifted, the L0. And we saw that this has some substructure, right? In the last lecture. And here I also draw one module. So that's in the other weights. So this is one non-trivial module. There would be 2 more modules which are like here, but they don't talk to the other one. So I just draw 2 modules. And you see the short screening is living in this module. And let's now a little bit see what this picture wants to tell us. So if you recall your formulas from last slides, you could in principle compute several of these screenings. I mean, let's for example start with here. So I hope now this works. Let's see. So this is e to the 2 over square root 2. So this is e to the square root 2. Here, this is what's called W minus. We'll see why. And now let's apply the screening, the long screening square root 2 to e to the square root 2. And as I said last time, we take the residue of y of this and y of this is, well, z to the square root 2 times e to the, oh, there's a minus here, minus 2 square root 2 times e to the 0. And then here is z to the minus 2. Let's see, and now I messed something up. Why did I mess something up? Ah, because it's square root 4. It's square root 2 times the root. Square root 2 times the root. Well, let's do it again. So now all I have to know, this was the formula I had last time in the general case. So now this starts with z to the square root 2 alpha with minus square root 2 alpha. There you have e to the square root 2 alpha. And then you have derivatives, right? Z to the square root 2 alpha minus square root 2 alpha derivative. And here now you have to add this. So this is e to the 0. And now let's compute what this is. So this is 4. So it's minus 4. So you see the highest term that you get is a z to the minus 4 term. And if you want to get down to the residue, which is here just an integral power. So you want the minus 1 term. The z to the minus 1 term will be here the third one. So times some polynomial in degree 3 times e to the 0. That's what you get. You can compute what it is. Some derivative, some combination of derivatives. And if you see, this is exactly you landing here below the unit 1, 2, 3 below. So you're landing here. So you can really compute those. So the long arrows are the long screenings, and the short arrows are the short screenings. And now you see the short screenings have a kernel. So this is this light gray guy, and they have a co-kernel because so this on the dark gray is non-zero, and you see that the long screenings act here, and they want to be a three-dimensional representation of SL2. So that's exactly the part where you get a section in the bundle. So here you have a three-dimensional representation of SL2. Here you have a one-dimensional representation of SL2. Here you're going to have a five-dimensional representation, and so on. So in particular, there is this three-dimensional representation where here's W minus, here there is W0, and here there is W plus, and this is an SL2 action. And this is what's called triplet, and that's where the name triplet algebra comes from, right? So you have the Virasoro algebra, which is in this kind of the W algebra. So this is the Virasoro algebra here, extended by a three-dimensional representation of SL+. So that's very explicitly you can compute each of these arrows by hand with the formulas I gave. I think for this one you need one formula more. So this is how explicitly the triplet looks like. Any questions to this? We should stay with this a bit. We have time. So it's a vector space where I come up with endomorphisms. Some endomorphisms give me an SL2 action. Some endomorphisms give me a Nichols algebra action. I take the kernel of the Nichols algebra action. I can compute piece by piece. I know always, that's the nice thing in some physics way of thinking, everything commutes with 5 different actions of stuff. So the short screening commutes with the long screening. That's why everything has the two representations. Everything commutes with Virasoro. That's why we don't get individual elements, but those are all Virasoro submodules, right? They're all sort of big chunks, but they cannot be composed because they are modules under the Virasoro action. There's classification of these modules. So it's the W algebra in this case. So I have the W algebra, I have the V algebra action. It's just like the minimal thing you can build. In some sense, right? If there is no more questions, then I would go a little bit off on a tangent. Because actually I wanted to do this in the first lecture, but there was not enough time, and there was a good thing to just leave it. But I think now it fits very well, and we have enough time. Because it came up in some other talks, maybe not directly, but so I want to a little bit say a couple of words about what the TFT picture should be. I mean, there is no TFT. It's non-semi-simple. We have problems with certain stuff is 0, but there is some derived proto version, and I want to maybe just have a couple of slides about this. So this is some recent work. So just to recall how much of a TFT we have in this case. So that's not the TFT part of it. So Lubashenko has established that we have a space of conformal blocks. We can define a space. So given a category, we can define for each surface of genus G with n punctures decorated by element in the category. So this is now a non-semi-simple modular tensor category. I can define this space of blocks. So this is the tensor product of the labels, and here's the coend of the category. So the coend is a typical guy that you get in contact with if you do non-semisimple theory, because in the semi-simple case, it's just the direct sum over xi star xi summed over all simples. So this is the typical thing that in the semi-simple case, you mean summing over all simples. Like S matrix or something is defined on simples, basically because of that. So now if it's non-semi-simple, this is more complicated, because in some sense, it's the sum over all tensor product of any indecomposables, but they are like stacked into each other, and you somehow have to divide out these identifications. So it's somehow you imagine you do this for all modules, or maybe for projective modules, but then you divide out stuff because there's identifications. And so just to have an example for the people more from Hopf algebra side, and it's somehow orthogonal to the other example, if C is rep H for Hopf algebra, maybe non-semi-simple, then what this is the dual of the Hopf algebra with the co-adjoint representation. So it's in fact the Hopf algebra in the category if you transmute stuff.
Can you write this for what should be possible?
Yes. I zapted it.
I think he wants you to write it now.
Now. So actually, parts of it actually I can. So more or less how this. I mean, of course, I can write down the co-adjoint representation of the small quantum group. But what it is so it's more or less it's a block decomposition, right? The block decomposition is S goes from 1 to 0 to P. And 0 now 0 and P are special, so let's maybe skip 0 and P. Those are the projective simples, and then it's something like you have 2 times, now I'm using a Satz notation because I want to remember, 2 times the unit object, and then 2 times the partner of the unit, which is these are in the principal block, and then there is other stuff. It's like this. So I think it's weights up to S or something. So it's more and longer numbers of simples. So those are the only ones we're interested in always. That's why I remember them. And then there's some projective. So there's a projective of 1, and again stuff, I think going up to S half or something like that. So it's like a formula like this. But it's written in articles of that. I think maybe you can say an article where it's written. In which article of you is that written, spelled out?
No, it's not.
It's not published. Okay, but we know.
No.
Okay, so now I know which one I talk about in 2 slides. Okay, so as I've known that for a long time, but maybe it will appear in our article. But I thought it's in some other articles. So that's, I mean, you know this. It's work. It's hard work, but it's known.
So can I ask a question?
Yeah, please.
So I would have guessed that the coend would be the full space of the bulk conformal field theory.
Yes.
Where you have sort of all your projectives kind of. You have like a holomorphic action for one BOA, and then the action of the other BOA then links all the projectives up together.
Somehow that's what it is. Yeah?
It will be regular. It will be like regular bimodule for this.
It's more like this, right?
And then you take a joint of this regular bimodule. We are in category of representation, not bimodule.
So it's more or less like this. It's projective dual and projective, but then you have to divide out stuff because projectives are not simple.
Okay, so I mean,
So somehow it's like that.
we wrote down conjectural pictures for what this should look like back in 2013. And it's basically like a ring where
No, but it's different. I think it's different.
it's not that.
It's not that.
Yes, sir.
I will compare now.
Take all my responsibility. It's not that.
Okay. So
It's
the
related.
character of the coend is not modular invariant.
I would say, yeah, it's not clear. I mean, there is action of functions.
They add up to one.
Yeah, I know that. That's why I'm asking what's different.
I mean, the structure, right? I mean, characters and structure. I mean,
Yeah.
as a model, it's different. It's not that.
This is why I'm trying to understand what exactly you're saying. So I'll wait until you write it up.
Comment?
Yeah,
This
please.
is not the bulk algebra.
Ah.
It's what we get from the bulk algebra when you apply the forgetful functor from the center to the category itself.
Yeah. But I thought the structure would be preserved, but apparently that's not correct.
Can you say it again?
Sorry, I thought that the structure, just as a bimodule, would be preserved in some sense, but that's not true apparently. So we'll wait and see.
Okay, so there's this coend. And using that, you can just come up with a definition. And I say this sentence a little bit too often, but it's the only thing you can.
Do you really mean the identity with x plus 1? Or but what is the module x plus 1? Is it projective or not?
Tensor unit.
No, x plus 1 is the tensor unit. And this is the simple in the block, and there's some projective. So there's simples sort of in some constellation, some combinatorial, and then some projectives. Yeah.
Okay, but then it's not the projection.
Okay. I don't know the bulk field, so
Yeah, that's what I said.
okay.
So it's not.
Yeah, we'll
How
compare.
does it come that it's simple? Yeah.
Oh, you have to compute.
I mean, it's a joint representation. A joint representation is projective even only if algebra is simple.
That's the center, right? I mean, we don't see if it's in a projective or not, but the simple
Generalization we restrict to one
comes up because we have center.
just simple times projected. But what we're writing down is the binomial whole thing.
Yeah.
And so I think I understand what you're saying. So probably we're right.
So what you're writing is an regular bimodule.
Mhm.
It's projective,
I
right?
understand.
But when you go from regular bimodule or the center of the category back to the category, it becomes something.
Yeah, this is just a power category. That's the problem.
Okay, but this is for me. This is very interesting to have these sort of different inputs. So we can come up with this space, which is basically more or less writing down the only thing you can write down with this data, and also it's what you expect from Lusztig and Turayev. And then you have to, and that's what Lutsenko did, and this is a quite complicated construction. You have to basically write down how the mapping class group of this really acts and with generators, using the braiding, the twist, and so on. So you use all the structures you have, and you define an action of the mapping class group. Notice caveat: this is not a full TFT, right? So somehow it's only the mapping cylinders. So we don't know what to do for a general case in the non-semi-simple. I mean, there's approaches with modified trace, and there is, but it's not clear what the complete TFT sort of is. At least not from this picture. I think if you have punctures with projectives, then Azad can tell you what it should be, but you cannot glue and stuff. So some things are complicated. But here, sort of, you see the mapping cylinders at least, or from the physical perspective, you see how if you act on your two-dimensional space with diffeomorphisms, how that sort of acts on the state space. Yes, and of course, the second caveat is that this space is usually so here. So in particular, when you look at the torus, right? That's what you assign to the torus should be now the characters. And if you write down exactly what the torus gives you, this is 3p minus 1 dimensional. Let's go through it briefly. So what the torus is assigned to is this representation. This is a representation of the mapping class group of the torus and of SL2, because SL2 acts on the category of symmetries, counter action. SL2, and what this decomposes is this work by Azad and other people, as you see, this is on these initial papers, is here p-dimensional representation, which comes from this S matrix. So that's basically SL2 affine. And then there is this two-dimensional, this is this one here. There is this two-dimensional guy, which has trivial SL2 action and the standard SL2Z action. And then there is a second summand, which will disappear in a derived setting. The second summand here, which is the projectives. So these are these guys here, which appear for all S, not just for the good S. And this is a cosine representation of the S matrix, it's somehow related. So this is how the state space looks like, the block space looks like for the torus. But this is 3p minus 1 dimensional, but there's only 2p simple modules. So if you compute characters, you sort of not get everything. On the Hopf algebra side, it's the same. You have class functions, so somehow this would be the class functions on the Hopf algebra, but not all class functions come from characters of modules. This is a semi-simple feature, a non-semi-simple feature, yeah?
Upper speed just means
Yeah. What?
upper speed.
Dimension, yes.
Dimension. Here, the two should be upstairs.
Outward.
Yeah, thanks. I have more typos on these slides than I anyhow have. I'm sorry. Yes, this is C2. This is CP minus 1. Dimension, exactly. And they also check that the mapping class group action in these two cases match. And also you can come up with pseudo characters which somehow come by you take in decomposables and you modify your traces in a smart way to come up with more class functions. So that's what is the result for SL2. And now there are several bugs that work because we are in a non-semi-simple setting, right? The Cohen is more complicated. We don't have enough characters. These things are more complicated because we are in a non-semi-simple case. But now, because we're non-semi-simple, we have another thing that we can do. We can derive stuff. And that's what we're doing now. So what we have established, so first in our work on Hochschultopology of Hopf algebras, which I think in hindsight, one should not read anymore, but it's like in a sense of everything is written down with cycles for the Hopf algebra, just for the totals. And then you see that there's a bigger picture behind it, which now it's just a long, like a little book, like this, what is it? Springer Briefs in Mathematical Physics, I think, will appears, I think, now at the moment. So it's on the archive for some time, but it's so this is in this we have basically just taken this definition, this previous definition here, and replace Hom now by X. And now, of course, you have to prove that there's an action of the mapping class group on this higher X group. So it's a non-symmetrical category. We have X laying around. Why not use it? So basically, the construction goes as follows: you drill another hole and you put a projective resolution, and then you take the cohomology of this complex, and then you have an action of a higher mapping class group, and then you have to prove that up to homotopy, sort of these factors down to the mapping class group you want. You have to prove that anything you do that involves this guy is sort of homotopically trivial. So you get a sort of derived version of this Lukashenko construction in general. And what is now also nice is this is infinite dimensional, but it's modules over what you assign to the sphere. And now the sphere is not so trivial, because what do we assign to the sphere? To the sphere, we assign the X algebra of the tensor unit, which is usually like a big commutative algebra, right? This is actually this Coulomb branch that appears in several theories.
What is this for?
I can tell you. So for triplet, luckily I used my time here to work on this article with Azad. That's why I have all these formulas in by heart. So the X algebra, I think it's even written on the next slide, but that's why I never does. The X algebra is C0, C3, 0, C5, and there is this SL2 action that you could take. So it's 1-dimensional, 3-dimensional, 5-dimensional.
So it's even part of symmetrical polynomials, right?
Exactly, it's even part of symmetrical polynomials. So it's generated more or less, it's generated by these guys, and these guys are in the second X, and you can see this is a Gerstenhaber-Lie algebra that you get from basically from the proper group of the big center. This is where this comes from, right? So this is what we have, and yes, let's now compute what happens for the triplet. So for the triplet, if I compute these cohomologies, and this is what I just did with Azad for some time, the last half year or so, you get the following result. So here in even cohomological dimensions, it's basically the same formula as above, just there is this Cn plus 1, which is just the action with this X algebra, right? So I have the 0 piece just multiplied by this X algebra. So that's kind of the boring part. But notice that the projective part disappeared. There's no P plus 1 anymore. Sorry, here. There's no P plus 1, would be only for n equals 0. It disappears in higher because it's projective, right? But then there is a new guy in odd cohomological dimensions. It looks almost the same, but the C square is different because it's now this. We should have maybe some color. So this here is actually our C square 1, and this is our other C square. And this is different because this is again this modular action that we had. This here is standard modular action and trivial SL2 action. This here is trivial modular action and standard SL2 action. So it's very different. Basically, this one consists of bottoms and tops of the projective, and this one consists of left and right. And this you get. So, and how can we understand these new contributions? And I think this is a very neat picture. So how can we understand these new contributions? We can understand them as follows. Let's take the torus with one puncture, and this puncture decorated by this one, which is together with the tensor unit in the principal block. So this is sort of another representation, but it's in the same block as the tensor unit. There's extensions between these two. So this space here is Z of sigma 1, 0, and this X. Let's just do it with X. Here there is an action of the mapping class group of genus 1 with one puncture, but it factorizes to an action of the mapping class group with 0 puncture, more or less because the twist of this has to be 1 because the same block is 1. So the mapping class group action of this is actually torus without puncture. And now what we can do, we can now glue to this not an element of the X algebra, but we now also have X between 1 and this X. So it's like a torus, we're decorated here by 1 and here by X. And I can glue this on, which means taking the cup product in cohomology. I can glue this on, and then I have a torus with puncture 1 in cohomological degree odd because this guy has convertible degree, same formula as here, but for odd. And that way I produce sort of new contributions in high convertible degree. So they come from punctured tori with stuff in the principal block. And if you use the X, you somehow get cup products that are in the block space again. I think that's a very nice picture. Yes, and that's how you get it. Any questions to this? Because then I will continue with different stuff. Yeah. What? Tensor, yeah. And this is basically the cup product with this. This is C n plus 1, right? There's a trivial part which you just get because, so somehow this is now, I mean, this is of course a word that we cannot justify. And there's work by Schweigert and Boyke who try to do this, not try, they do this homotopy coherent. So I'm just talking about cohomology. You can think about homotopy theory in this context. And so the hope at the end would be to have something like a derived TFT, but we're not in any way there yet. But that's somehow the idea behind it. So there's you can derive everything and you get new contributions from what happens. Yes. And of course, it's interesting what happens on the view A side, right? You would think that you do something like take a projective resolution and then compute pseudo characters in this projective resolution, and somehow you get new classes in this cohomology. So sort of modular forms. I mean, this looks like a representation of a modular form. There should be modular forms associated with what's here, right? And probably that's how you get it.
Your last paragraph should odd and even be swapped around, maybe. I mean, we certainly don't have a self-extension for any.
0, 0. Yes, sorry. Because I switched to conventional. Yes. Is there more questions on this? Then I will continue. Now a little bit with plenty of time. What I consider to be this sort of a little bit big picture about screenings. So that now stops triplet. So this is something I would like to, if you see stuff like that, so either regarding Coulomb branch or in Chris Negron's talk regarding this having derived stuff up here and stuff from cohomology, or in Dupai's talk, or so I would be happy to see if you can somewhere use stuff like this. So if you see this sort of derived picture anywhere up here, and if not, then it's just a nice sort of game you can play with the cohomology of such a semi-simple algebra. Yes. So now let's start with non-semi-simple extensions of MTCs and UAs. Modular tensor categories and various algebras. Yeah, how do I want to put this? So my feeling coming from the classification of Hopf algebra, so that's what like where I grew up in this graduate school in Munich, grew up in quotation marks, where people worked on how to classify pointed Hopf algebras, and that's what's still very much contributed by in Cordoba, for example. Many people here are from that. The idea that you get when you start to learn tensor categories is at some point when you look at the examples, classifying modular tensor categories is a very hard problem. And if I put hard in red, that says I don't even think I should start thinking about it. So that's what I mean with hard. So there's other things that are also hard, but I dare to think I have an idea about it. But this is sort of let's not touch this. So modular tensor categories will be a very hard problem. Also, semi-simple modular tensor categories is also a very hard problem. So I thought very briefly about, because this was we did this in Munich. There were people doing this classification of semi-simple Hopf algebras of, I don't know, dimension 12 or something. And there's results, but it's very hard and out of my league, and use very different technology. I think you don't use Nichols algebras and stuff. It's more like you use the category, I think, actually, but you know much more about this than me. But so let's somehow make our life a little bit easier in a sense of let's do what we can do. So the proposition is somehow as a slogan, let's try to classify modular tensor categories with a given semi-simple part. So suppose I give you a semi-simple part, what are the modular tensor categories that can have the semi-simple part? And of course, it's not clear what I mean with semi-simple part. I hope it's a little bit clearer now. One example of what I mean is, let B be a Nichols algebra. It doesn't have to be a Nichols algebra, but that's the idea in mind. Because it's a nilpotent algebra that you can take. Now we can take the relative Drinfeld center. So we start with some semi-simple tensor category. It doesn't have to be semi-simple, but let's assume it is. And take representation of this Nichols algebra, take the center that constructs us relative Drinfeld center. And by construction, this U is Witt equivalent to C. And that's something Dimitri Nikšić told me, I think, 2 lunches ago. I was very happy after your talk to understand it from this perspective. So I added this to the slides. And also this. So it was a question?
No.
No, okay. So somehow you could rephrase that to, which is probably again a hard problem, are all modular tensor categories with equivalent to some semi-simple modular tensor category? So is there somehow, so what I want to do is somehow just explore the difference between these two notions. So I have a semi-simple tensor. You have to ask Dimitri, not me. Dimitri, is it expected that this is true or not? Tomoyuki asked.
I don't know. I mean, no counterexamples. I have no evidence in favor of otherwise.
I mean, if there is no bit equivalence, then certainly I cannot go there by my technology. So the question whether there is something out that is sort of purely non-semi-simple, I don't know. I have to say, maybe let's jump. No, maybe let's not jump. So, for example, when we do this procedure here for vect A, this category I always propose as like our simplest example, what this technology produces is, I think for me, it's now not hard to state this, but maybe some people on the MTC side were surprised. You can produce a lot of MTCs, non-semi-simple MTCs, namely the small quantum groups, this associator deformed small quantum groups that you need for the even root affinity, because here then the vect is as an associator. Also this in all super cases. So super Lie algebra at a root of unity gives you a modular tensor category if you do it right, if you start with the right modular tensor category here. Also for all guys in Heckenberger's list. So Heckenberger more or less wrote down what this quantum group would look like. He calls it U chi. You know, it's this big list that I had on the blackboard with all these Nichols algebras, diagonal algebras. Each of them gives you a modular tensor category. For some, you probably have to again start the right way to get the associator. That's why you cannot literally take those, but I mean, that's the main input. So you would take the Borel part here, realize it in a good modular tensor category, maybe with associator, and then take the Drinfeld center, so some modified version of this, which gives you a modular tensor category, not just a tensor category. So I have to say that they did not think about modular tensor categories. They always thought about tensor categories, so classifying Hopf algebras. There was never talk about modular and stuff. So how I come to this is basically to compare this to this Andruszkiewicz-Schneider program, which was very successful in the classification of pointed Hopf algebras. So very briefly, what is a pointed Hopf algebra? A pointed Hopf algebra is a Hopf algebra where the co-radical, which is the maximal co-semi-simple part, is fixed. In this case, in the easiest case, to be an abelian group. So you have, it's the same problem. Actually, I think even some article by Andruszkiewicz-Schneider start like that for Hopf algebras. I think that's where I have it from. So they say classifying Hopf algebras is hard. Classifying semi-simple Hopf algebras is also hard, but let's try to classify Hopf algebras with a given semi-simple part. And that's exactly what happens. So they wrote this article where they basically say, suppose it's an abelian group. So you always have, I'm not sure what in the category is the case, but for the Hopf algebras, you always have a designated maximal semi-simple sub-Hopf algebra generated by the co-radical. And then you always have a Nichols algebra over this inside the Hopf algebra. It can be trivial or it can be complicated, but this part is always present. And then you somehow go through all the Nichols algebras you have, and you have to prove somehow rather by hand. This is what Ivan does, for example, a lot. You have to prove by Ivan Anchiono, prove by hand that there is no more elements. But you can somehow do this. There's generic arguments. As soon as if you have the Hopf algebra fixed, you somehow can show that there is no more stuff in there, that this is contradictory. And that way, so what they actually did in their first article is they somehow restrict their abelian group such that only the Nichols algebras from quantum groups appear and prove the theorem, which I think is a very good theorem. And then Heckenberger classified all Nichols algebras, and then Ivan Anchiono proved sort of a similar theorem using now these Nichols algebras. So somehow for Hopf algebras, we have a statement like this, because we somehow know what the semi-simple part should be. But I cannot, I'm not in any way familiar enough with tensor categories to make such a statement in tensor category. That's why I sometimes ask people, what would you say if you have a tensor category? What is the semi-simple part? I don't know. It should be like the maximal semi-simple category from which you have a tensor functor, injective tensor functor there, a faithful tensor functor there. Yeah?
How is that with equivalence C between U and C? But how do you show that U and C are equivalent?
Because the center of rep BC is so because that's how you construct a relative center. So I cannot write. Let's raise the blackboard this time. We have that was too much power. So because I mean, what is the relative center? The relative center is exactly defined like this, that this box times C ref is isomorphic to the center. I mean, you take the center of B and then you somehow get rid of, right? I mean, the center of C is something like C box C ref. And somehow you take the center of B, which contains C, and then you get rid of the extra C that you have. And that gives you an equivalence of box, right? Is that correct?
I think so.
Yes. As I said, I mean, I added this sentence. I think the night after I talked to him.
So B, so what's the relation between C and B? Like B is the category.
So B is the category of modules over B in. I mean, as Hopf algebras, I can write all of this down. As categories, I'm learning the language since some time now, but maybe not enough.
But I mean, the relative center is not like the Linfeld center of an, which is like a predicated. Right?
Exactly, it's the centralizer of the image of this in this center.
Yeah, it is a theory.
Yeah, it's a theory of that. I cannot quote by heart where these things are written, but yes. So that's somehow the idea. So the proposition is to avoid these three hard questions. Although I'm very interested in seeing how you can contribute to this. So somehow for a class of tensor categories, we can say this, but by saying which class we mean, we somehow already fix that we have a semi-simple part. So somehow this is maybe avoiding the question. Maybe really it's a different question. But let's avoid these three hard parts. Then somehow it stands to, I mean, I just added this, so I cannot make any statements about it, but it stands to hope that somehow what this wants to say is, at least we can construct in this way more or less all with equivalences of semi-simple categories.
Does your statement also hold if your semi-simple part is degenerate?
I would have to think about this. Then becomes all these things become more difficult.
Your argument doesn't.
Yeah, I don't think so. I would always stick with MTCs because in the degenerate case, I have many more examples of this, and you can look at this under Schneider work. I mean, they classify tensor categories.
Yeah, but this gives you many more examples where you don't.
Many more examples. It's exactly that's a context.
But you don't see the width equivalence immediately. That's
exactly. So there's examples where you have like 4 Borel parts linked on their edges together, and you get an R matrix, but the R matrix is more or less just the edges linked together, and the rest is degenerative. So I would have to look at examples, but I think you get so that what they get as tensor categories is much.
Are they degenerate or are they not degenerate?
I don't know if they're braiding or if they are degenerate, but I think my gut said that they have a degenerate braiding sometimes, but I have to look at the examples. Most certainly, they are not degenerate. I mean, okay. So so this is now a category philosophy. Let's now switch to the VUA side. What is the VUA philosophy that I would have? Somehow these two developed in my mind parallel to each other. I cannot even say which one was first. So this is the category philosophy, and the VUA side is as follows. How can we construct VUAs that realize these non-semi-simple tensor categories? Assume now the same thing. So classifying VUAs is difficult, and classifying semi-simple VUAs is also difficult. So suppose we have a given VUA that realizes some tensor category C, which imagine to be semi-simple, doesn't have to be, but imagine it to be semi-simple for a second. Assume we have some realization. So for example, for vector A, it's a lattice VUA. For non-abelian groups, which we had in this Nichols talk, it's lattice orbifolds. For an affine Lie algebra, it's an affine Lie algebra, right? And you can also take a quantum group. It doesn't have to be semi-simple. A quantum group, then maybe some beta gamma system or the triplet itself. So you can ask what is like a tensor category sort of based on the triplet algebra. And now what we do is we consider screening operators for some modules we pick. We pick any modules we want and take screening operators. Those realize, if everything is subpolar and so on, realize the Nichols algebra. Of course, usually infinite dimensional, but if we can classify the finite dimensional ones. And now we take the kernel of these screenings. There should be a modular tensor category of representations of this. What is it? I can always play this game for every VUA and every set of screenings. I can ask, I mean, this may be a weird VUA, but it's going to be a VUA. What is a representation category? It should be a modular tensor category. And the candidate, I didn't put this as a conjecture because it's too bold maybe, but the candidate would be the only thing you can write down, namely take representations of this Nichols algebra in C, take the relative center, and this would be.
Why is it? Why is it natural?
Because I find it natural. I will give you some reasons afterwards, but so that's, yeah. So the idea is a little bit, it's like orbifolding V by a Nichols algebra. So if you do a group orbifold, you somehow extend by G rep and by G vect. And the effect, if you look in the examples, and I will show you the rest of the, somehow it's the same. So you add twisted sectors, but now not twisted by group elements, but somehow they feel like twisted sectors by the Nichols algebra roots. And then you add an action of the Nichols algebra, and somehow that gives you this double construction. So the idea is it's like an orbifold process by non-local screenings. So if you want to get intuition, I would think you go in 2 steps. You first say not group orbifold, but Lie group orbifold. Then Lie group orbifold should be expressible like a Lie algebra orbifold, right? I don't have to talk about Lie group, it's just a Lie algebra with the screenings. So orbifold by local screenings, and then you have somehow something very close. You have like a category which is like, not, I mean, it's not graded by the Lie algebra, right? But something like that. What I had on some slide, I want some infinitesimal version of this inner correspondence. You have some Lie algebra cross tensor category in quotation marks, which is just the Lie algebra version of the G cross tensor category for a Lie group. And now you want to do this for non-local screening. So now there's a breaking present, which is inside the category. So it's an extension of this category. You have a forgetful functor from the category, from the extension to the category itself, like this. And I want to just, so this is, I mean, I'm not claiming in any way that I can prove this. I'm not even claiming it's right. I'm just saying that's the only thing comes to mind. And this philosophy has some reasons why it might have a chance of being true, or at least generating right ideas. And I want to give you some evidence. So now I'm completely speculative, and I'm showing you some recent work with Thomas and Matt Ruppert, and I also show you how the triplet cases looks like. And maybe that's the only arguments I have. So first evidence is it seems like the only thing we can define in general. So I ask a general question, which is well posed for general VUA and a general screening operators. There has to be a general answer. I know this is a stupid algebraized answer, right? Of course, there can be a very non-specific answers in each case, but somehow it feels to me like there has to be some expression you can write down using the Nichols algebra and the tensor category, because what else do you have? But maybe that's too easy. Yeah, it's one argument. Then of course my guiding principle is that it specializes to the conjecture for the triplet or for this faculty-Bullian algebra, which we know is true for SL2. So in this case, it produces the equivalence. If you believe the philosophy, sort of, it's a special case. That's this. And also now, as I say, I will go a little bit. I told you that we have proven this tensor equivalence in this paper, and we are working now on a revised version that can take care of P also, but now with methods that I think are more general. And I will tell you a little bit about these methods because they are sort of. I will not tell you this proof, so I tell you the revised proof. It's very similar, but here we have some shortcuts because we didn't know some stuff. So I will tell you what I think how one should do it now in hindsight. We could rewrite the paper now in hindsight, but we don't. Maybe just to try the next case. And I think this is a very structural way of thinking about these things, and you think why it should be true in one places. And also in blue, I tell you some extensions of this, maybe more sophisticated, which could tackle higher cases. But I only want to print this in blue because I'm speculative enough. So now I'm talking about sort of this revised proof method that we're writing up at the moment. How does this go? So let's go very much one step back. So which structures do we have sort of from the start? So I'm always talking about orbifolds by Nichols algebras, that's philosophy, but this of course we don't have, right? What do we have? So what do we have is, let me use the following name for a trivial thing. So a current extension of a braided tensor category should simply be a choice of a commutative algebra in this tensor category, which has certain nice properties, which we have to fix in the next slides. But for example, A should be a simple algebra. If A is not a simple algebra, then things get more weird. And then what are all the functors we have? So we have our tensor category U. We have representations of A over U with a tensor product A. And we have the local modules. Somehow I'm trying to reverse the orbifold. And sometimes that's conceptually easier because there's no orbifold. You just do simple current extension. It's not a simple current extension, right? This can be an arbitrary algebra. And now let's fix all the data we have. So we have these 3 categories. This is a braided tensor category. This is a braided tensor category. This is just a tensor category. Here you have a tensor functor, induction by A. So if a module here, you can tensor it with A, it's an A module. Here you have the forgetful functor where you forget the action of A. It's just an object in U. This is just an oblex tensor functor. It's not a real tensor functor, right? Because you forget the A action. So because here you have a tensor product over A, you just have a tensor product in U. And you can compose, I will always write this because it has some meaning. You can compose this and this area, you get an oblex tensor functor here. It's written like Covermer for reasons that become clear in a second. And this picture I should maybe draw on the blackboard, because now I will modify it and have examples for it and so on. So this is now the rest of the lecture. I will talk about this picture. So if you have questions about this picture, so here we have B. So this is, we have A in U with a tensor product in A. And you have this. Forget A. You have tensoring with A. This goes to U. And here it's C. So other local modules. And here you have the inclusion, because local modules are in particular modules. And here you have this composition of these two arrows. I call COVID. Should not spell like COVID, but since COVID it reminds me always on that, but I kept the name anyway. It's Octobre-Novembre. But maybe it's fitting because basically we talked about this only over Zoom because it was during COVID. So yeah, so this is the picture we have, right? And of course, there's no accent. I call C, B, and U, and I will try to keep these letters, even though this is not usual letters for categories. U, of course, should be a quantum group, B, the Borel part, and C, the Kazhdan part. That's how I think about this. That's how you should fix these roles, no matter which categories they are. So let's now turn the two main classes of examples that we have. The one main class is with a vertex algebra. That's, of course, where this theory comes from, for a vertex algebra extension. So, of course, that's the other way around. So from the extension of vertex algebra, so V is larger than W. This is the wrong way around. For example, for an orbifold or for a free field realization, which we imagine as a Nichols orbifold or whatever it is, it's some extension. We can view the larger algebra as a commutative algebra over the smaller algebra. And then what we have here is representations over the smaller, more complicated algebra. Here over the larger, more easy algebra, like lattice VUA. And what we have here, I just put the name. What it is just this. So what it is, it's modules over the W, which have some intertwiner with V. So V and M have non-integer Z powers and logarithms, but there is some fixed intertwiner. So it's somehow twisted modules over V, which are ordinary modules over W. And twisted here, of course, is not intrinsically defined, right? For G orbifold, you can say G twisted modules. And for Nichols algebra orbifolds, maybe at some point we have some Nichols twisted module, but I don't fix it. So it's just a name for what this category is. It's a tensor category. In the case of a orbifold, it's the twisted modules. Yes. So this is the one example I have in mind. So you should keep these rows. So this here is induction. You have a module over the small VUA, you induce it up to a module over the large VUA. And in this case, you have, this is very easy. You have restriction. There's a module over V, this restricts to a module over W. So that's the. Now, for quantum group, this looks exactly the other way around. And I have to say that I thought about this also a long time with Azad. So we did some stuff. Actually, I think, if I remember, it's the first time I met Thomas. Thomas was in Hamburg. Azad introduced me to him, and we talked about pictures like this. There were some questions we had. So for the quantum group, there is the dual Verma module. And what you have is here representation of the quantum group. Here you have representations of the semi-simple part. This is vector A. And now it's a little bit difficult. What is this? So this is now representations. I have it written here. It's representations over the dual Verma module inside the quantum group. So it's UQG plus Hopf modules. If you don't know what Hopf module is, it doesn't matter. But if you know it, it's Hopf modules. So it's somehow two structures at the same time with a tensor product over this algebra. So that's maybe a weird guy. But there is a non-trivial equivalence to the negative part of that quantum group. So then the tensor product is the one you think. So it's like that's like those two are Morita equivalent. So somehow this category, this algebra is Morita equivalent to this algebra. It contains a Heisenberg double that gets cancelled. But writing it like this has the wrong tensor product in the sense that it's not a fiber functor to vect, and writing here is the right tensor product in the sense that it's a fiber functor to vect. So that's why I say Borel, right? Borel, Kazhdan, quantum group, right? And now it's the other way around. Here, of course, you induce to this big algebra, but then you go through this equivalence. What you actually do is you restrict. That's something very confusing. It's exactly the other way around on the quantum group side. And the other way around also, what you do here is you have this big module, which consists of chunks of A, and you restrict it. But if you go through this equivalence first, then this is actually inducing up. So this is inducing up a module over the negative Borel. So the composition of these two is actually the co-Verma modules. So dual Verma modules. Yes. So these are two different pictures we have in mind. And questions so far? And now I think in this situation, there is stuff one can say, and people have good papers on this, and we also thought about some things. But now in this project with Thomas, we want to go sort of one step further. Now the question is, what do we know that is not usual? I mean, what is not something that we have in all of these situations? And I like to introduce the following name for this. A current extension, which is a complete general object, is said to admit localization if there is a tensor functor is important, localized that goes here in the other direction, which is inverse to the inclusion of local modules. So I want to look only at cases where I can take a twisted module in this general sense, or for orbifolds, if you want, a twisted module and sort of by force make it local, somehow kicking out all the twisted part of it. And of course, this is usually not what you have. So there's many counterexamples. In fact, most lattice extensions, for example, of lattice VOAs do not have this property because it's a splitting property. It basically means that the new lattice is somehow a direct summand of the old lattice in some sense, or the discriminant of it. Or most G orbifolds do not have this property. But when you think about Andrew's talk yesterday, those exactly have this property. So he said several times, basically, the orbifolds we look at now are more or less trivial. I mean, not trivial, but I mean, somehow they are easier than other orbifolds. And exactly in this sense. So it was very nice that you had to talk yesterday about it, because I got the point. So the point is somehow, for example, all the twisted sectors more or less look the same as Abelian categories. It's not some weird orbifold. It's a very easy orbifold in some sense. That's why it looks like a Drinfeld double. And that's exactly the intrinsic property. In particular, what you have is a forgetful functor here. So I should be able to imagine U as a Hopf algebra over C, which usually I can't. But C can be your base category, and usually this is not a Hopf algebra over this. But for Drinfeld centered it is, and basically Andrew told us the Hopf algebra in these cases. So there's many counterexamples, but I want to focus on these cases, and I think want to develop this theory more, yes?
So by density you mean it's strong monoidal?
Yes, strong monoidal.
And only one-sided inverse.
Just one-sided inverse, yeah. So you should basically imagine you localize a module by force, and it's not, careful, because we had some discussion, it's not taking the local part. It's more like really localizing. It's like, I will see examples how this goes. And how can we prove such a property? And there's basically three different ways how one can prove this. So if we know these twisted representation category well, then we can prove this property. Right? I have always to look at this. If you know B well enough, then we can prove such a property. For example, the case that would be relevant to us is this case semi-simple extended by nilpotent. So if there's like this subdivision in these two cases, because if we have the statement that all simple modules are local, all simple modules, which is true for a triplet, for example, which is not true for usual orbifolds. But then we can define localization just by taking the graded module with respect to the socket filtration. So somehow if the twisting comes from a nilpotent thing and the category itself is semi-simple, then somehow they don't talk to each other. And that's why I hope you get these like trivial orbifolds in a sense. So much easier than you would get for finite G, because you have this property. Also, now more going on this side, and this is more involved, but we have in the application we need it. Suppose we have a quasi-fiber functor to C. So suppose I have a guess for a functor like this. So I have a guess for the composition of this, if you want. Suppose I have a guess for this. How can this be? Well, in the example that we have, triplet or we see we have enough fusion rules, so we can guess a forgetful functor to vect. I mean, we can guess what should be the dimension of this, the dimension of this, the dimension of this, so it's compatible with the fusion rules. And now we can do the same thing graded. So we guess which graded weight space this module would correspond to and check that the fusion rules satisfy this. This is somehow, if you look at triplet, you immediately guess what is the corresponding weight decomposition, but you just check by computing fusion rules it's true. So it involves much knowledge about the fusion rules here, but not the associators and stuff here, just the fusion rules. So suppose you have this, then we have this, what I always call associator lemma. You have in this paper, if you have sufficiently many different A, so if you have the situation several times, such that the product of this A is a projective module, so somehow if you can cover your category by situations like this, then you can prove that in fact you even have a fiber functor. So you can prove that the associativity does not destroy this. So you somehow prove that this which you just got by guessing dimensions, is in fact a tensor functor. And you do this model in an abstract way. You fix a representative in the, maybe not so important. So that is, I think, for the people who know Hopf algebras, if you look at these quasi-Hopf algebras that you get, it's interesting that the associator, it's a complicated associator, but the associator involves only the group part. So this thing is a quasi-Hopf algebra, but it's not more quasi than the Cartan part. And that's exactly this property. So there is an associator, but the associator is already here, and it doesn't get worse here. So this is a Hopf algebra sort of over this, an honest Hopf algebra over this. That's what this lemma says in general. And then you can use old work by Takeuchi and Scriabin to push this fiber functor that you have here to a fiber functor here. And I have to say, I only know this for Hopf algebra, so more or less we can use this if we know all these categories are categories of Hopf algebras, which we know in the triplet case, but I don't know in any way how this looks for arbitrary categories. So there should be some theory like Takeuchi theory, which I think is very, very important. In Hopf algebras, we need this for a lot of deep theorems, and I do not have any idea in this context how to do it. Actually, it should just, you should repeat the arguments. Some arguments are categorical, but some are very algebraic. And I think this would be a very interesting little project. Maybe not little, I don't know. But so this is great theorems, but we have them for Hopf algebras and for quasi-Hopf algebras, but there should be some categorical meaning of what they do. And then third, for the Hopf algebra people, what does it mean for a quasi-Hopf algebra? You know, here's some quasi-Hopf algebra or Hopf algebra, here's some Hopf algebra, here's some Hopf algebra. Here you have some inclusion, which means there's a quotient Hopf algebra. And it means exactly that this is a split extension. So it means that this Hopf algebra is not some arbitrary complicated Hopf algebra, but it's a semi-direct product of Hopf algebra here with another Hopf algebra. So it's again a splitting condition. It's the fact that the Borel part splits. It is not just quotient to the Cartan part, but it splits. It's a semi-direct product. So that's sort of exactly so those are three different ways of proving its localization, or scenarios in which you have localization. Yes. And now, good. So now that we have localization, and as I said, I think we don't understand the categorical fallout yet well enough. So in some sense, if one would have enough time for this, one should probably imagine really writing up, suppose I have an arbitrary current extension which is localized or has a localization. What are all the categorical stuffs I can say? So suppose there's enough finiteness, then blah. Suppose A is a Frobenius algebra, then we have these. Like you should have all these standard statements that these guys have. If you only have Hopf algebras, but we don't have to do this because we have what they have. But anyway, so now what we have, if we have localization, let's now see the fallout. So if localization holds, then the category B. Then we have a tensor functor down here. And what this means is B is a Hopf algebra. I can write B now as a Hopf algebra.
So what is localization again?
This is from the previous slide. So if you have this yellow arrow, so if you can make a twisted module into a local module by force. If there is a tensor functor in the other direction, or if a tensor functor is in this direction. And we just saw three different sort of scenarios or proof strategies how to establish the existence of this yellow arrow. And now we see what is the fallout of this. Maybe localization is a bad name. I just don't know a better one. I mean, in no way it's meant to correspond to localization algebra geometry. It means like untwist a module. Make it by force twisted. Like for example, go to a graded module which has no twisting anymore. No drawdown blocks anymore. So suppose I have this yellow arrow, then immediately, and that's what it's designed for, is B is now representations of some Hopf algebra B over C. Because there's a functor in this direction, not in this direction. And from a view A perspective, it's funny because now from all perspectives, it somehow doesn't really make sense. It all is nice, but it also somehow is not what you would think about. So from a view A perspective, what does this mean? This means that your category of twisted modules is realized as modules over a Hopf algebra in your category of local modules. That's something you usually don't have, right? I mean, this picture here is completely standard for view A, but the other picture is somehow not. It's a little bit, it comes from this functor that you have that you for orbitals don't have. But in the case we have it and we have it. So if localization holds, then the category can be realized as representations of some Hopf algebra in the category, which is the category of local modules, or the category of the free filterization in the application. And actually, it has more structure, of course, because it's a Hopf algebra in this category, but here it's the regular co-algebra. So it actually has a structure in this category. But if you push it down with this localization function, it becomes a Hopf algebra here. So what this means, it's a module here, so it's a co-algebra in this category, or if you dualize it in algebra, but a Hopf algebra. Somehow it's a very, very non-local. It's like the most non-local module you can have in some sense. The regular representation. So it's like a very, very long, very, very unlocal module. And I will show you an example in a second. So now somehow what we have to now find is what this B is. It's a well-posed question to say, given a localization extension, what is this Hopf algebra B? And if we know all of this as Hopf algebras, then Skriabin gives us a formula for B. And the co-invariance of this with respect to the co-ideal subalgebra that this was built from, reduced module. So Skriabin gives us a formula for B. If we know all these as Hopf algebras, which we don't in our application, but just saying. So we have to find B somehow. And then what we have is, and this is, I think, a very nice result then. Actually, it's not even so extremely difficult with the right, so I'm skipping all technical stuff, right? But the right assumptions, for example, if all is finite, modular, and so on. Then I immediately know that U is the relative center of B with respect to C. So I've reconstructed U. And somehow it's much easier to think about B and about this Hopf algebra B, because it's a split case, than about this complicated quantum group U. So somehow in this first article that we have for P equals 2, we first somehow classify all tensor structures in certain scenarios like this, and then we think which of them can be braided and so on. And later we realize that we don't even have to do this. You just have to do this like on this side, which is on the VUA side more complicated, because you don't even know what you would put here. I mean, it's like Nichols twisted modules or something, but you can define it, but it doesn't have an intrinsic VUA meaning in that sense. I mean, it has, but not really interesting one. Not one that can work with. But somehow this category is much easier to fix. There's no braiding to fix. For example, we found a family of solutions for tensor categories, which are different than ones we want, but only one of them is braided. And this is no accident because it's this one. It's the Dirichlet center. So somehow it's much easier. You like work only in the half of the quantum group, and the rest you get for free. And this is actually not a difficult statement. I mean, it's application of standard things that people do when they work with centers and so on. You have to use a relative version and add some stuff, basically. So somehow this should convince you that somehow if I have situations where I have localization, and I've hopefully motivated that these Nichols cases are, because they are like non-semi-simple extensions of something semi-simple, they have a chance of having this property, which orbifolds don't have usually. Then there is some B such that this is true. Which one is the B is not clear at this point, right? And now we want to convince ourselves why B should be the Nichols algebra of strings. And for this, let's look at an example. So let's look in the triplet algebra over the vect. How does B look like? I mean, I can write it down. So this is the triplet, this is vect A, and those are now representations over the triplet which have an intertwiner from lattice view. So that's our definition of a twisted module in that sense, right? It has an intertwiner from V, but it's not the proper module over V, it's just a module over W.
Simon, I'm sorry, I'm confused about previous slide.
Yeah, please.
So your category like this curly B, right?
Yeah.
It's the category of modules of B and C. It's not a subcategory of C, right? It's a quotient of.
Yes, but you have both directions errors.
Okay. That's what you say that our localization
Exactly.
holds. Okay.
That's the point. Otherwise, it would be much
Because otherwise it's not clear what the relative center is. Okay. Thank you.
So very, very good point. This is a point. I mean, it seems like this is just a technical point because otherwise you can't define the center. But with the analogy from the orbifolds, I want to say it's not just a technical point. Like if you don't have localization, the category can be much more complicated. We have examples in Z2 orbifolds that do not look like this. But if you have this localization, then it looks like Andrew, and then it looks like this. And we don't, yeah. So now in this example, how do these modules here look like? So those are somehow modules. Morally, they are modules over the lattice VOA, but they are twisted modules of lattice VOA. But if you restrict them, at least they are on the kernel of strings, they are local. And how do they look like? Well, the easiest thing you can think about is just a lattice module. It's an honest lattice module. This is a module that's here. So this is, of course, a subset here. It's a local modules. But now I can build more complicated modules, which look like this. So I have a big lattice VOA module, the one with the shifted weight, the one with the shifted weight, and I write suggestively the screenings here. What this means is, if I have logarithms in the intertwiner on this, which give you terms here, and I have logarithms in the intertwiner on here, which give you terms here, right? So it's more or less a picture like if I do this, then it's more or less a ZV plus screening of V. So it's what you would write down for an orbifold Bernoulli algebra intuitively. So it's like it's non-local, and it's non-local because it has logarithms where the screening appear. And in fact, so that's how it looks. And of course, you see immediately this is exactly the modules I had in my first lecture slides, right? This is how they look like. And they should be viewed and axiomatized, but we don't have this, as sort of screening twisted V lambda modules. I mean, somehow it's clear what you do like this, right? But we don't did this so far. And the conjecture that I would a little bit boldly even, but maybe pose is that if W is the kernel of screenings and that everything's subpolar, then this B from before is exactly the Nichols algebra screenings. And there is not just the evidence from the example, but the evidence is actually we have half the statement, because these guys, of which Jürgen Fuchs is also a subset of, have written down how you get the point was to get the logarithmic twisted modules, the logarithmic modules over the triplet. And what they would done would take lattice modules and sort of glue them together and then twist the action, this delta deformation I mentioned. So they get projected modules over the triplet. But you can still view them as modules over the lattice VOA, but then they are twisted. So somehow if you keep the full structure, you have this construction exactly outputs these modules. So that's what you should do. And of course, again, I have a big counterexample to this, namely W2,3. W2,3 module is a non-exact tensor category, and U is slightly bigger than the Drinfeld center. There's a quotient to the Drinfeld center, but U is slightly bigger.
So what is subpolar?
Subpolar was this condition that the MIJs, right, that the sum over all IJ in J of the MIJs is larger than minus J plus 1. So the poles are not so bad. So you have to check that the screening momenta, for example, are not negative definite. Remember, we had this negative definite case here. This cannot happen. Otherwise, you get larger algebra. Maybe then again it's true. But
Logarithmic.
yeah, what is it?
Logarithmic.
Yeah.
What is logarithmic?
So the formulas I don't know by heart, but so what you do is, I think I do it even by heart. So this is established in these articles. I just use it a little bit upgraded. That's why I don't put it as a theorem, but as a statement. So what you can do is if you have a screening acting from some module to some other module, then you can look at this module with modified action. So this is a module, so maybe you should take W1 and W2. With a modified V action, which goes as follows. So AZ modified is the same as AZ. And now you replace A by e to the log Z screening plus, and then some signs Z to the n plus 1 higher modes of the screening, something like this. A, Z. So you deform literally your module action. I mean, literally, you write down a new module action, which somehow now has a term that goes from here to here. Before this is direct sum. And what they use it for is, and this is established, and many people use this, I think, for the triplet, for example, what they use it for is now this is called delta in the physics equation, I think. This deformed module is a proper module over the kernel of screens. But it's more. It's a module over, still a module over V, but one with logarithms. It's a twisted module. And if you check this condition that I had, no, it's gone already. Yeah, it's gone. So if you check this condition, exactly what happened. But if you put y of a e to the 2 pi I z, if you do a continuation around, what you get is exactly here, right? I mean, you just get you add the screening, right? because here is this logarithm.
And this conjecture implies that as a heuristic equivalence to
If you know enough stuff in advance, yes. And that's what I want to say. So how is our so this would be, of course, the cool final part. But let's now go for the last minute. Oh, it's already 30. Just how we usually do it by hand. I mean, how we now do it by hand, not knowing this conjecture, is as follows. So what we did in the paper and what we now do in the new paper is we know, so assume a lot. We know the category is representations of the quantum group as an abelian category. We know this from people. We know that the Frobenius Perron dimensions match. So we know it comes from some quasi-Hopf algebra. We know enough fusion rules to prove this associator result and compute the induction functors. We know enough to compute this as an abelian category, or use Scriabin's result would be the dream, but we don't have this. Then we can try to classify, we know B as an algebra, but not as a co-algebra. We try to classify co-algebra structures. For SL2, we do this by hand, but it would be cool to use this Andruszkiewicz-Schneider method. So you can actually do this, I think, and get all possibilities. And then this proves with the last statement that this is really this. And this is how it worked for triplet SL2 and for triplet equals. That's it. If you know such stuff, yes. No, this I need because I don't know what I said before. This is a strategy how we prove it for P equals 2 SL2 and how we prove it now for SL2P. Yes, and of course I have the question. We want to know if this approach that we already have implies Kazhdan Lusztig if we know the abelian category and we know it is modular. So that should be doable. The conjecture I put is maybe difficult, but this should be doable. We need a definition of a twisted VUA representation. We want to check some niceness assumptions are equivalent, being simple, being Frobenius, being cleft. So we want to generalize this work. And still we have no clue what 2,3 does with this non-exact tensor product. So that's of course larger. Yes. Thanks a lot for the attention.
I think we have already inundated Simon with questions, but there's time for one or two more. It seems like the inundation is complete.